In this video, we are going to discuss how Edwin Hubble used his data along with those of Henrietta Levitt in order to find the ratio between the distance to the Andromeda Galaxy, commonly known as M31, and the Small Magellanic Cloud. So, in 1925, Hubble published measurements of the magnitudes of the stars in the brightest spiral nebula in the continent of Andromeda, which we now know as the Andromeda Galaxy. It's also called M31 because it was the 31st catalog entry in Charles Messier's catalog. At this time, it was not known whether these are our own galaxies or external island universes. Recall from the reading that Shapley thought they were within our own galaxy, and Curtis thought they were island universes. Below are plots of his data with regression curves. Find the ratio of the brightness of physically similar stars located in the Small Magellanic Cloud to the same ones located in M31. Now notice that these have only one line first. That one line is the peak brightness because that's all he published. So when I plotted them up in much the same way as Levitt did, these here, okay, follow a line, these follow a curve, but they're the peak brightness. So to correspond peak brightness to peak brightness. Notice something else. The period of all of these stars are between about 15 days and about 45 days. There's nothing like the period of Delta Cephei. So when we go back and we look back at Levitt's plot, which we're going to be correlating these with, then you can see these go up to about 120 days, and so maybe we'll use about this part of the plot, okay, rather than that part. So, given that right in the middle is about 35, 25, 30 days, something like that, then maybe we'll pick something about like that to here. So, why don't we say, hypothetically, imagine something was, let's see, this is 25, 35, 26, 27, 28, 29. So this 27, 29, 31, 33, and 34. So 27, 29, 31. So it's be right around 30 is right around there because it's 0.4. You see that? So a little bit this way. Maybe that's better. Maybe it's more like here. That looks pretty okay. And then we can find that same where it crosses the line. Remember, notice the scatter is significant. Okay? So we're going to make sure that we compare line to line. So you can see that if one of these period 30, not Cephei, but if a period 30 variable star were in the Andromeda Galaxy, it would have a magnitude of about 18.55. So we'll mark that. Now we'll use this one too. let's do something similar here and see what we get. The logarithm is 1.477, and you can see that this is 3, 4, 5, 6, 7, right? So if this was 3, 1, 2, 3, 4, 5, 5 between 0.2. So 0.2 divided by 5 is 0.04. So 1.33 plus 0.04 is 1.37. Okay? And then we can take 2.5 from there, and we should be right around here somewhere. So you can tell that in one case we found it to be about 18.6, the other case to be 18.55. So we can decide which one. It's up to us which one to use. They're about the same. So now we know that in Andromeda, a period is 30 days. Variable will correspond to a magnitude of 18 point. Well, we just picked a number in between for now. Okay? Now, the same thing in the SMC is so the period was 30 days. We'll find 30 here, and this 30 should be right here in this line. Should mark right there. And that looks pretty good. And if we do the same thing over here with our with the logarithm of 30, which as we call was 30 log 1.477, that would be somewhere around here, right? So 1.4, 1.5, 1.477, somewhere around here. So you can see this point here is about there. So you can see we measure something a little bit different both places. One was 12 point, wherever that is, 12.25, and this one was 12.75. So, yep, that's about right. So we have 12.7 here and about 12.3 here. I said 2575, that's about right. So if we average those two, we get about 12.5. So why don't we call it 12.5? So now that we've seen that, we can come back to here and we can say if a period 30-day variable star were in the SMC, then its magnitude of we just said 12.5. Okay? So, we now know that if we had a corresponding object in both, the difference would be about 6 magnitudes. 18.5 minus 12.5 is about 6. So, we now know that the magnitude in M31 minus the magnitude in SMC is which is 6.07. Okay. And given the error bars in here, these were significant in here and here, right? This is, you know, the errors, there's some error in here. Now, what does that mean? That means we have to use that same formula that we used before for magnitudes. So if we recall, that formula was so we could use this form of the formula like we did before, or we could use this form or this form or this form. It does not matter. So let's pick that same form we used before right here. And given that it's asking for the brightness between the SMC and the Andromeda Galaxy, we're going to call 2 SMC and 1 M31. So the brightness, if a period equals 30 days were in SMC, divided by the same period, the same thing, if in M31. Now remember, it's not the brightness of the whole SMC versus the whole M31. M31 is much brighter in total luminosity, and so when you put the two together, I'm not sure which is actually brighter in the sky if you added everything up. But what matters for this is the brightness of corresponding objects. So that equals 1 divided by 100 to the negative 6.07 divided by 5, which is equal to 100, 6.07 divided by 5. And we know that this has to be bigger than 1, so that's what we have here. So what we're going to do is I'm going to clear this out. I'm going to say 100 x to the y, open parentheses. If you don't put parentheses in, it's going to mess you up in terms of orders of operation. So 6.07 divided by 5, close parentheses, 1.214. Now remember, only about 1 or 2 of these digits is significant. So we can now say that a corresponding object in SMC is 1.2 times brighter than 1 in M31. And now we can use this, just like we did before, to figure out how far away the ratio of distances are. So we now realize that we picked 30 days. Why? Because it was the middle of our data. It shouldn't matter which time period we pick, but it's always better to pick it in the middle of the data. We're making the assumption that the two objects have the same luminosity because they're hypothetically a 30-day period, with a 30-day period because they are a 30-day period Cepheid variable, so therefore everything physically should be the same, because that's the premise. And now we have the ratio to the distance to M31 to the distance to the SMC. And now we're going to have the brightness of our corresponding objects. The ratio of that is 1.214 to 1. So this would be 1.214, and that would be 1. Now, we will have to write down the inverse square law of light, just like we did before. Remember, if you have a light source, such as one of these stars, the light goes out every which way, and so it spreads out over a full sphere. So we know that the brightness is proportional to the luminosity over the distance squared. And then recall, we solve for the distance by multiplying both sides by the distance squared and dividing both sides by the brightness. So we got r squared is proportional to the luminosity over the brightness. And then we took the square root of both sides, and we got r is proportional to the square root of the luminosity over the brightness. Now that we've gotten this, we can then say the ratio of two distances is equal to the square root of the ratio of two luminosities divided by the ratio of two brightnesses. So we're looking for the ratio distance from there to there. So we will put M31 here, and we will put the SMC there. And then we will have the luminosity is the same, so that's a 1-to-1 ratio, because they're the same. And then what goes down here is a 1 to 1.214 ratio. So clear 1.214, and now we're going to take the square root. We get 1.102. And then we only know this till basically a couple of digits. So the distance to M31 is 1.1 times the distance to the SMC. And there we have it. So now we have solved this question. And in order to solve this question, as we recall, we had to come back and we had to look back at Edwin Hubble's data and compare them to Henrietta Levitt's data from before. So in order to find this ratio, Hubble had to not only take new data, but had to compare it, to compare those data to Henrietta Levitt's from before. Okay, thank you for listening.